I'm your host, Dr. D. Welcome to Math in the House. Today, we're doing Math Analysis, Chapter 7, Section 4, Part 1 of Vector Applications and the Dot Product. I'm your host, Dr. D. All right, so equilibrium in vectors means that the two vectors have a sum of 0. So basically it's like the tug of war between two teams where it's equal force, opposite direction, there's no motion at all. So here's an example. One vector is right 50 and down 20. The second vector is left 50, up 20. Well, when I add 50 plus negative 50, negative 20 plus 20, I get 0, 0. So equal magnitude, opposite direction make vectors in equilibrium. So an example of that is a bird flying 20 miles an hour against a 20 mile an hour wind will have a velocity relative to the ground of 0 miles per hour. When I skydived, that was the velocity of a canopy is about 17, 18 mile an hour forward. And so if we were in a 10 mile an hour wind, then we landed against the wind with about a 7 or 8 mile an hour forward velocity, which made it a nice, easy landing. If we're landing into a, let's say, 18 mile an hour wind, and we're moving 18 mile an hour forward against the wind, then we're at equilibrium. Okay, so cruising onward. Let's say we have two forces, force 1 and force 2. What I want is a third force that will provide equilibrium with the whole system. Okay, so force 1 is 50 newtons at 150 degrees. So notice 150 degrees, 50 newtons. And force 2 is 30 newtons at 50 degrees. So 30 newtons, 50 degrees. Now what we want is the force that provides equilibrium. Oh, incidentally, I just tossed this out without thinking about it. The capital N stands for newtons, and it's a metric system unit of force. And you really need to say it as if you have a little bit of a head cold. So it's like 50 newtons, and it's a force. And practically no one even knows what it means, even people from France. Okay, so we've got these two forces. Now what we want to do is find the x components of each force. So I take my first force and I go 50 cosine of 150. That's the x component of my force to the left. Now 30 cosine of 50 is my x component of force 2. So I take x plus x equal total x. Then I want my y components of both forces. So I take 50 times sine of the angle plus 30 times sine of the other angle. Now when I add those two up, I get 48.0 newtons. Now, I want the See, what this basically says is my resultant force is 24 newtons to the left and 48 newtons up. So that's what we have right here, going up and to the left. So the magnitude of this force, I take my x and I square it. I take my y and I square it. I add them, take square root of the whole thing. That gives me the magnitude of the entire force. So that's going to be 53.7 newtons. And now I need the direction of that force. Well, the direction is going to be the inverse tangent of y over x, 48 over negative 24. Now, notice when you go to your calculator and you go, well, 48 over negative 24 is negative 2. So you go 2, change signs, inverse tangent, you get negative 63.43 degrees. So negative 63 degrees. Well, the problem is your calculator doesn't know the difference between a positive divided by a negative or a negative divided by a positive. It looks at them the same way. So it's going to give you the negative 63 degrees. Well, if you want the actual angle of those two forces, you have to add 180 to it. Because remember, tangent is negative in the fourth and the second quadrant. So that's all your calculator knows is it's in one of those quadrants. Well, it gives you the one in the fourth. So you have to add 180, and so you get 116.565051177 degrees, which rounds to 117 degrees. So we have a total force of 53.7 newtons at 117 degrees. So if we want equilibrium, we need the 53.7 Newton force in the opposite direction. So what's the opposite direction from 117 degrees? Is add 180 to that, and it's 297 degrees, which is basically the original angle that you first got, which was the negative 63 degrees. But remember, we don't want negative 63 degrees, we want 297. So you can see that the two red forces combine to make a force up here. Now, the equal but opposite force would be going down the other direction. So the purple is the equilibrium force.
Bam! Do we have that in a Christian school?
That's a hold on. Now, the next principle that we want to learn here is called the component of u along v. The component of u along v. Now I have vector v and vector u. Now normally what we're interested in vector u is its x component and its y component. But here, I don't necessarily want the x and the y component. All I want is the component of u along v. And so what I would do to show that graphically is I just take the tip of u and drop a line down to v perpendicular. So the component of u along v is that distance right there. Now, how do we get that? Well, first of all, the symbol that describes this is COMP of u. And which direction? The v direction. See, if I wanted a force in the x direction, then I would go force in the x direction, or a force in the y direction. So if I want a component in the v direction, That's what I do, a component along v, a component of u along v. And note one other thing, that the component of u along v is a scalar quantity, not a vector. All it is this distance here. We're going to look at vectors in a little bit, but right here, this is the component of u along v. All right, so how do we get that? Oh, actually, yeah, I already showed you how we get it. We get it by going the magnitude of u times cosine of the angle in between u and v. That's it. Notice if I look at this triangle here, then the component of u along v is the adjacent side. So adjacent divided by hypotenuse. What's the hypotenuse? It's going to be the magnitude of the u vector. So all I do is get the magnitude of u times cosine of the angle in between u and v, and that's the component of u along v. And like I said, it's just a distance. Okay, so take a look at a few different situations. Here's our original situation where theta is between 0 and 90. And notice the component of u along v ends up being positive in this case because it's going from bottom up. Now, if theta ends up being bigger than 90, so in other words, we just move theta past 90, so it's u is going the opposite direction of v. So now, notice the component of u along v is going to go backwards from the point of intersection, so that makes it a negative value. Now, let's say theta is 0. That means u and v are going the same direction. Well, that means the component of u along v is just the magnitude of u. Simple. Okay, now, what if theta is 180? So I go all the way the exact opposite direction. Then the component of u along v is going to be negative magnitude of u. Now, what if the angle is exactly 90 degrees? Now the component of u along v is 0. Because if you have a 90-degree angle, then u doesn't exert any force on v left or right. So that's it. All right, now we have an inclined plane. And this is similar to what we were just dealing with. You've got the classic example of a box or a crate on a ramp. Now, first thing we do is we ignore friction. So we say a 200-pound crate is set down on an ice-covered ramp. So we have no friction at all. And the ramp is inclined at 20 degrees or 25 degrees. So there's theta is 25 degrees. Now, notice the forces involved here. If, I would just go this way. First thing, we have the red force, which is the force of gravity on the crate. And gravity is going straight down toward the center of the earth. Now, the second force that we have here is a force going down the ramp. Like if you were standing on this ramp, if you could be standing on the ramp with 0 friction, then that box would exert a force on you because it's falling down the ramp. Now the other force is if there was a scale on the ramp and the box was exerting a force on the ramp itself, that's the green force. So 3 forces: gravity. Now gravity is what makes it go down the ramp, and gravity is also what makes it go onto the inclined plane. But so basically the gravity is being reduced into 2 components, the force down the ramp and the force onto the ramp. And we have F sub n because it's called force normal. Now, when you make this triangle of forces, there's going to be an angle here between gravity and force normal. That angle will always be the same angle as the incline. So if I look at this triangle here, the force down the ramp and the force parallel to the ramp and the force normal to the ramp are perpendicular. So there's a right triangle, and gravity is the hypotenuse. So if I want the force parallel, that's going to be gravity times sine of theta, because opposite over hypotenuse will give you the blue. And if I want the force normal, then I go gravity times cosine of theta, because the green is the adjacent side. Now, we are only going to be dealing with the force parallel to the ramp in this course. But if you take a physics course in college, you're definitely going to get force normal. So I wanted to let you know what that is. Also, the other thing I wanted to show you is gravity is a force, because it's a weight is a force. So the 200-pound crate, 200 pounds is the force the crate is exerting on the Earth. So a 200-pound crate is set down on our ice-covered ramp, and the ramp is inclined at 25 degrees. How much force will it take to keep the crate still? In other words, what I want is the equilibrium force that I need to apply up the ramp to that box, to the crate, to keep it still. Well, the force parallel is going to be 200 times sine of the angle, which is 84.5 pounds. So that means I'm going to have to push on that crate with a force of 84.5 pounds to keep it on the ramp. Now, if I push with more force than 84.5 pounds, then I'll be pushing the crate up the ramp. Now, this is why ramps are handy, because notice I have a 200-pound crate, and I can move it upward with much less force than 200 pounds. Okay, cruising onward.
Bam! Do we have that in a Christian school?
That's annoying. Hold on. Work. Work is the force in the direction of motion times the distance traveled. So work is FD cosine theta. So force times distance times cosine of theta. Now distance times cosine of theta makes it in the direction traveled. Now, there are two units of work. One unit is good old foot-pounds from the United States of America. And the other unit of work is Newton meters from France? Yes, France. Okay. Foot-pounds, United States. Newton meters, metric system, the rest of the world. So, let's take a look. We're going to use units from the United States of America for our example. Okay. When Bob mows the lawn, Bob is 100% American. Okay, thanks, Bob. All right, so Bob mows the lawn. He exerts a force of 50 pounds at an angle of 30 degrees with the ground, with the horizontal. If Bob covers 1,000 feet in his lawn mowing, how much work did Bob do? Well, here's Bob, and he's pushing the lawnmower, and he's pushing 30 degrees with the ground. So here's Bob's force right here, and it's 30 degrees with the ground. Well, we don't care about the downward component. Like Bob's actually pushing that lawnmower down toward the ground a little bit. We don't care about that. That's not work. The work he's doing is just what work he's pushing the lawnmower in the direction traveled. See, it's not traveling downward, it's only traveling along the ground. So, this force in the direction traveled is the force of his 50 pounds times cosine of the 30-degree angle.
Bam! Do we have that in a Christian school?
That's annoying. Hold on. Okay, so how much work did Bob do? Well, work equals force, which is 50 pounds, times distance, which is 1,000 feet, times cosine of the angle, which is 30 degrees. So that's going to be 50 times 1,000 is 50,000 times cosine of 30, which is square root of 3 over 2. And so we end up with 43,301 foot-pounds. So Bob did a sizable amount of work mowing this lawn. But you didn't have to do any work at all because the amount of distance you moved while you were writing these numbers and letters out was negligible. So that's it. 43,301 foot-pounds. All right, cruising onward. Now, let's say we have a force of 3, 4. In other words, 3 pounds to the right, 4 pounds up. And we have a distance of 12 feet to the right, 5 feet up. So in other words, the force vector, 3, 4, is being applied to a distance vector of 12, 5. How much work is being done? Well, you know that work equals force times distance times cosine of the angle. We need to know what the angle is. Okay, so to find the angle, we say theta of my force is inverse tangent of y over x minus the inverse tangent of 5 over 12. So I'm going, first I want the angle of the force, which is inverse tangent y over x, minus the angle of the distance, which is inverse tangent 5 over 12. And so now I end up with 53.13 degrees minus 22.62 degrees. So the theta I'm interested in is 30.51 degrees. That's the angle in between the force and the work. Now, the component of force along the distance is what we're looking for. That's what work is force along a distance. So that equals 5 times cosine 30.1. That's my force. Well, let's back up for a second. How did we get 5? Well, we need to get the magnitude of this force. So what's the magnitude of the force? It's going to be square the x, square the y, add them up, take square root. And it's a 3, 4, 5 right triangle, so force is 5 pounds. Now, what's the magnitude of the distance while we're at it? Well, if it's 12 right and 5 up, then I have a 12, 5, 13 right triangle, so magnitude of my distance is 13 feet. Okay, now we're ready to go. So the component of force, the long distance, is going to be the magnitude of the force times cosine of the angle in between, which is 4.31 pounds. In other words, if I drop the perpendicular down onto the distance, then the force along the distance is 4.31 pounds. Now, the distance is 13 feet. So I'm going force times distance. So 4.31 pounds times 13 feet is 56 foot-pounds. Now, basically all we did was FD cosine theta, and F is the magnitude of the force, D is the distance, 5 times 13 times cosine of the angle, which is 30.51 degrees, ends up being 56 foot-pounds. Okay, now there's a shortcut to doing that, and that's called the dot product. Here's what the dot product is. Let U be the vector AB. So it's A to the right, B up. And V is the vector CD, C to the right, D up. Now the dot product of vector U and vector V is just going to be vector U dot vector V. Now what do? All we do is multiply the x's, A times C, multiply the y's, B times D, and add them up. That's dot product. And so you could say that work is FD cosine theta, or you could say work is F dot D. Same thing. So let's look at from F dot D. Well, remember, the force is 3,4 and the distance is 12,5. So all I do is multiply the x's. So 3 times 12 is 36. Then I multiply the y's. 4 times 5 is 20. 36 and 20, 56 foot-pounds. So notice F dot D really equals FD cosine theta. Okay, one more. The dot product of U and V can be used to find the angle between the two vectors. See, if we know that U dot V equals the magnitude of U times cosine theta times the magnitude of V, well, if I want to know what cosine theta is, all I'm going to do is divide out the magnitudes. So that means cosine theta equals the dot product of U and V divided by the magnitude of U times the magnitude of V. And if I want to split it up, I could say it's vector U divided by magnitude U dot vector V divided by the magnitude of V. So this is cosine of the angle. Well, so that means the angle itself is going to be the inverse cosine of vector U divided by the magnitude dot vector V divided by the magnitude. All right, so let's try an example problem to demonstrate that. We want to find the angle between vector U, which is 815, and vector V, which is 724. Okay, so vector U, the magnitude is going to be square the x, square the y, add them up, take square root. And you know 8 squared is 64, 15 squared is 225, 64 plus 225, 289, square root of 289, 17. Or you also know that 8, 15, 17 is a Pythagorean triple. Then we take vector v, square the x, square the y, add them up. 49 plus 576 is 625. Square root of 625 is 25. Or you know that 7, 24, 25 is also a Pythagorean triple. All right, so we have the magnitude of u and the magnitude of v. So vector u is 8, 15. Well, if I divide vector u by the magnitude of u, then instead of 8, 15, it's going to be 8 17ths, 15 17ths. Now, vector v is 7, 24. Well, I'm going to divide vector v by the magnitude of v, so it's 7 over 25, 24 over 25. Now, I want the dot product between these two vectors. So what do? Well, I just multiply the two x's, multiply the two y's, add them up. Now, you would think you'd need a calculator for that, but certainly you wouldn't, because you know 8 times 7 is 56, and 17 times 25. Well, how much money do you have if you have 17 quarters? You have 425. So 17 times 25 is 425. Now, 15 times 24. Well, that sounds tough, but really it's not. 15 is 3 times 5, and 24 is 3 times 8. So 15 times 24 is just 9 times 40, which is 360. Piece of cake. Okay, so we've got the product of the x's plus the product of the y's, and that's going to be 56 plus 360 is 416 over 425. Now we need the inverse cosine of 416 over 425, and that ends up being 11.81 degrees from your trusty calculator. Now, if we want to verify that, we could put those two vectors on a graph and notice here's vector 8, 15, and here's vector 7, 24, and what we're trying to get is the angle in between them, and clearly 11.81 degrees is reasonable. So basically all we're doing is taking vector u, divide by its magnitude, vector v, divide by its magnitude, do the dot product between the two, which means multiply the x's, multiply the y's, add them up, take the inverse cosine, bam, we're done, game over, have fun with these.